So if you've spent any time at all looking at the world of modern technology, I mean, AI, cloud computing, these huge data systems, it can feel, well, less like a science and more like just an overwhelming flood of stuff.
Oh, that feeling is incredibly common. The jargon alone can make you feel lost.
Right.
But that's what we're doing today. We took the source material for this deep dive, the essential guide to computer science fundamentals, and our goal wasn't to, make a bunch of flashcards. It was to build a kind of internal GPS.
Exactly. Our mission is pretty straightforward.
Yeah.
We're pulling out the fundamental structure of computer science, the real architecture underneath everything. And then we'll get into the best practical advice for learning and how it all fits into, the big tech forces of 2025.
And this isn't about memorizing syntax, not at all. It's about learning the structure of how to think, how to solve problems effectively.
Okay, so let's start with that big picture definition because I think that really anchors the whole conversation.
It does. At its core, computer science is really the study of how we use computers to solve problems. And these problems are getting more and more complex. It connects pure theory, physical hardware, software, logic, all of it.
And you just can't stress enough how important mastering these fundamentals is. When we talk about Core CS, we're really talking about the engine behind everything that matters today.
Everything. The efficiency of a huge cloud platform like AWS or Azure, the security of our online world, the very structure of AI and machine learning.
It's all built on this. If you get the fundamentals, you basically gain control over this whole world that's built on code.
Exactly. So let's dive into that foundational layer. The structures of thinking. I'm talking about algorithms and data.
Algorithms, that's where it all begins, right? I mean, everyone sort of knows an algorithm is a set of steps to solve a problem.
Sure, but the real insight, the thing that makes computer science so challenging and so rewarding, is the constant search for efficiency.
Okay, so it's not just about getting an answer, it's about getting it in a smart way.
A smart way, a fast way, a cheap way. Efficiency determines the practical limits of what we can even do. A great algorithm can solve a problem in seconds that might otherwise take, well, a lifetime.
Wow.
And it's not just about speed. It's about saving money, reducing energy use, making sure a system doesn't just fall over when it gets hit with a lot of traffic. It's the difference between a real system and just a cool idea.
And of course, you can't have these steps, these algorithms, without something to operate on. That brings us to data structures. I love how the guide calls them the shapes of information.
That's a perfect way to put it. The shape actually dictates how fast you can do things. The trade-offs are everything.
So like an array is great for grabbing something quick if you know where it is.
Exactly. Near instant indexing. But they're rigid. Then you have something like a hash table, which gives you lookups that are almost immediate, which is critical for things like caching systems.
But there's a catch, right?
There's always a catch.
Yeah.
With hash tables, you have to worry about collisions.
Yeah.
So that requires some really clever design.
And then you get into the more complex stuff for modeling the real world, like trees and graphs.
Yes. Trees give you that hierarchy you need for, say, a file system or a database index. And graphs, well, graphs are just essential for mapping networks. Think social media connections, Google Maps routing, anything with relationships.
So choosing that structure at the very beginning of a project, that's a huge decision.
It might be the single most important one you make. The structure is the speed.
Okay, so we had our steps and our shapes. Now we need the tools to actually build with them. Programming languages.
Right, and the advice from the source here is great. Don't get caught up in the language wars. You really don't need to know 5 different languages when you're starting out.
That feels like a relief to hear.
It should be. What's more important is understanding the principles behind the language. Ask yourself, how does this language manage memory? Do I have to think about it? Or is it automatic? How does it handle errors? How does it organize big programs?
And that question ties right into architecture and systems. This is the layer that makes the theory actually, run.
We're talking operating systems, the actual computer architecture, virtualization, cloud infrastructure.
Okay, let's pause on that. Virtualization versus cloud. They seem so similar.
They're related but different. Virtualization is the tech that lets you run, say, multiple operating systems on one physical machine. Cloud infrastructure is the management of all those virtual resources at a massive automated scale. You have to get that architecture to understand how a system can handle millions of users.
And finally, the lifeblood of pretty much every app of databases.
You need to store and get your data back fast and safe. The source material draws a really clear line here between the two main models.
The old school versus the new school.
Sort of. You have relational databases, think structured tables, very strict rules to keep data consistent, They prioritize integrity. And then you have the more flexible NoSQL models, which are built for huge amounts of data coming in really fast. They prioritize scale and speed over strict structure.
Knowing when to choose one over the other sounds critical.
It is. It defines what your application will be good at.
Okay, so that foundation leads us right to the big frontiers. I mean, what's the point of building this beautiful system if it's completely vulnerable? We have to talk about security.
We do. And the guide is really blunt here. Security is non-negotiable. Every system is a target now. Period.
We're moving beyond just fixing bugs. It's more like active adversarial thinking.
That's the mindset. You have to know the core concepts. Encryption to protect data, strong authentication to prove who you are, and maybe most importantly for developers today, threat modeling.
Threat modeling is so fascinating. It's like you have to think like a hacker to protect your own system.
You do. You have to anticipate where it will fail before you even write a single line of code. It's proactive.
Oh,
And you need a solid incident response plan because the question isn't if you'll have a security issue, it's when.
that idea of learning and adapting, it takes us right into artificial intelligence. Traditional programming is all about following a set of fixed rules.
Right. It's deterministic. You tell it exactly what to do.
But AI flips that completely. It lets the machine learn the rules from the data itself.
That's the paradigm shift. AI systems are amazing at finding these tiny, complex patterns in data, making predictions, and then changing their own behavior over time. They automate without you having to write a million brittle if-then statements.
I have to ask, though, with all this chaotic big data feeding these AI models, does that threaten to make all those clean, foundational CS concepts, I don't know, irrelevant?
That's a great question. But it's actually the opposite. AI is built entirely on those foundations. The source had a fantastic insight here. It said, computer science isn't about teaching machines how to think.
Okay.
It's about figuring out the underlying structures, the algorithms, the data representations that make thinking and learning possible in the first place. AI is just pushing us to invent even more powerful structures.
That's a beautiful way to connect the theory to the practice, and it's a perfect transition to the practical side of this. For you listening, if you want to build that thinking muscle, what's the recommended path to start?
The guide is very practical here. It says start with data structures and algorithms. They are the single best way to improve your core problem-solving ability, no matter what you end up doing.
And don't chase the new shiny language every 6 months.
Please don't. Pick one robust language, maybe Python or Java, and just grow with it. Really learn it deeply.
And the key is to actually use it. Learn by doing.
Absolutely. Build small things. A
Mhm.
simple API, a little command line tool, a to-do list app. It doesn't have to be fancy. These little wins build your intuition. The guide calls it strengthening your gut.
I like that. What else?
Go deeper than the code. Learn the basics of how a computer actually works. Processors, memory, the operating system. And here's the one most people skip. Spend a lot of time just reading other people's code.
Why is reading code so important?
Because when you write code, you're just expressing your own ideas.
Yeah.
When you read good code, you learn about style, clarity, structure.
Yeah.
You learn how other smart people solve problems. It's a huge shortcut to getting better, much faster than just writing alone.
That makes a lot of sense. That understanding is also key to staying motivated, right? When you hit those learning walls.
It is. The guide has some great advice on mindset. First, you have to break the subject down into tiny, understandable pieces. You can't learn databases and security in one weekend. It's impossible.
Just pick one small thing.
One small thing. And second, follow your curiosity. Learn about the things that genuinely interest you, not just what's on some checklist. That's what keeps you going.
And what about that balance between theory and practice?
Oh, it's crucial. Too much theory and your knowledge is just abstract. You can't build anything. Too much practice without theory, and you're just copying and pasting code, totally lost when something breaks because you don't know why it worked in the first place. You need both.
Let's talk about the transformation that happens. What changes in your thinking as you get better at this stuff?
It's profound, really. You stop seeing code as this weird magical text. You start seeing systems, you notice patterns, you start anticipating problems before they even happen.
So complex systems become less scary.
Much less scary, because you understand the parts. Ultimately, you become independent. You trust your own process instead of just looking up a tutorial for every little thing.
That independence is so important. But even the best experts watch systems fail in the real world. So let's shift to that. Why do systems fail and how do we fix them?
This is where it gets really interesting. The source material points out that most technical problems, they aren't actually caused by the technology itself.
Wait, what?
The tech usually works. The failure comes from choices that were made long, long before anyone started coding. The guide lists 6 really common non-technical reasons for failure.
Okay, let's hit a couple of the big ones. Number 1, bad system design.
That's the root of so much technical debt. The initial architecture just can't handle the real world, and everything slows down to a crawl.
And number 2 seems so simple, not enough documentation.
It sounds boring, but it's a killer. As systems grow, people forget how they work, and trying to fix a bug in a system with no documentation is like doing surgery in the dark. You'll probably make things worse.
Another one I saw was about misaligned expectations.
Oh, that's a classic. The leaders want it fast, the engineers want it stable, and the users just want it to work perfectly. When those 3 things are out of sync, people start taking shortcuts.
And those shortcuts are often in security, right? Number 4.
Always. Security gets sacrificed for speed. Everyone knows that pressure to just ship the feature, but that one little shortcut is often the exact vulnerability an attacker will find later.
So if these are the problems, what are the solutions? The guide talks about building resilient habits.
It's all about discipline. First, think about your goal before you pick your tools. Don't let some shiny new technology dictate your architecture.
And like documentation as you go.
Yes, not as a chore you do 6 months later. And do load tests way, way sooner than you think you need to. Don't wait until launch day to find out if your site can handle traffic.
And I thought this was great advice. Have weekly technical cleanups.
Little cleanups. It stops that technical debt from becoming this huge mountain you can't climb. And when things do fail, and they will, you have to do postmortems without blame. Focus on the system, not the person.
The data on this is pretty shocking. Something like 72% of system failures are caused by these kinds of human or process mistakes.
That's the number, not hardware failing. And think about the cost. In big companies, something like 60% of engineering time is just spent on maintenance, just keeping the lights on, not building anything new.
So how do you fix that?
You automate what you can. Automated testing alone can cut major outages in half. And those no-blame postmortems. Teams that do them regularly improve about 30% faster over 6 months. Clarity and consistency, that's what builds resilient systems.
Which brings us right to the 2025 landscape. What are the big pressures shaping the field right now?
We pulled out 4 major forces. First, obviously, is smart automation fueled by AI. Second, just the unbelievable amount of data flooding every single system.
Third is the huge pressure on privacy and security.
And the fourth one is this constant demand for more speed. We need things to happen faster than our hardware, which is limited by physics, can actually go. We're always pushing against physical limits.
So that really frames the central question for 2025, doesn't it? How do we build systems that are reliable and consistent when everything around them, the data, the threats, the hardware, is constantly changing?
And part of the answer is understanding why different experts seem to disagree on how to do that. Why do researchers, product leads, and security engineers all sound so different?
It's because they're optimizing for different things. A researcher sounds cautious because their job is to find absolute proof. They want rigor.
Exactly. But a product lead sounds impatient because they live on market deadlines. They need to ship, they prioritize speed.
And security engineers, they can sound so negative.
Because they live in the worst case scenario. Their entire job is to imagine the most catastrophic failure possible. They prioritize reliability against active threats.
So to get the full picture, you, the listener, need to be able to synthesize all 3. You need the theory, the speed, and the resilience.
That balance is really the sign of a mature, well-informed technical mind.
So what's our big takeaway from this deep dive? I think it confirms that computer science, at its very heart, is about finding those elegant structures that make complex thought and scalable systems possible.
And good engineering, whether you're working on AI or a simple website, is about clarity, consistency, and long-term thinking over just getting it done quick.
If you master these fundamentals, the algorithms, the data structures, the disciplined approach to building systems, you're not just ready for 2025, you're ready for whatever comes next.
Well said.
We'll leave you with one final thought to chew on from a quote in the source material. When you automate a process, you show what you never fully understood about it in the first place. So as you see all this hyper-automation and AI, ask yourself, what widely used automated systems today might be revealing a fundamental lack of understanding or maybe a lack of security discipline in their original design? Go explore that. We'll see you next time on The Deep Dive.